All right, thanks, gang. Let's do a quick ramp problem with a spring. So let's start out with the knowns: a ramp of angle theta, a block of mass m, and a spring with spring constant k and relaxed length d naught. Right? So this is the relaxed spring to start off with. So I think all of our answers are going to be in terms of these things. Actually, I guess we also need a, let's let the ramp just go on forever. So the first, this is at time 0 with an unstretched spring. Following me so far? Got it? Okay. So now let's go to time 1. We'll compress the spring down to some length d. All right, and then ask maybe when we release it, the block is going to go shooting up the ramp. Let's ask how high up the ramp it'll go. Sound like a plan? So maybe at t final, the spring is back here and relaxed. It's not doing anything anymore. The block has gone all the way to some d final. And if it's the final height, then what can we say about the block? Velocity is 0. So this v final is equal to 0. Okay. And also, at this moment, I think it's important to say we're going to release the block from rest. So v1 is equal to 0. Okay. So it's actually from this time 1 to this final time that we're going to use a conservation of energy problem. This has the added hiccup, though, that we have two kinds of potential. There's a spring potential in this problem, but also as this block moves up and down the ramp, what other kind of potential is changing? Yeah, the gravitational potential. Yeah. Okay, so let's look at if we can assume first no friction. Then we have that the change in energy is equal to 0. There's no non-conservative forces doing work. And so therefore 0 is equal to k at the final time minus k at time 1 plus u at the final time, subtract u at time 1. All right. Now, like I said, though, this is a little bit tricky. There's two kinds of potential at both of these times, so we need to think about that. So coming down here, we can say 0 is equal to, let's look at k final really quickly. What did you say about the block at its maximum height? Nice. So that's k final is 0. And then at time 1, what did we say? We released from rest. So there's no change in kinetic energy here. All right. The final potential energy, like we need to deal with two things: u final spring plus u final gravitational, and minus u at time 1 for the spring and u at time 1 for the gravitational potential. So let's take these four pieces one at a time. Finally, the spring here is doing nothing, right? The spring is back to its relaxed length. Right, so are you scared of that spring? No. How much potential is it storing? None. Good. The final well, actually, let's get back to gravitational in a moment. The initially, though, the spring is compressed, right? So this spring is storing energy, is ready to do work. So how much does it store? That's our 1/2 k x squared. So u spring equal 1/2 k x squared. But we need to remember that the x stands for the amount that the spring is stretched, right? Or compressed. So how much is the string compressed at time 1? D tells me the total length at time 1. d naught minus d. That's good. And it doesn't matter which one's which because we're going to square it. Okay, so we've got d minus d naught squared. Okay, so that goes there. All right, now to do the gravitational potential energies, we have a choice to make. Where is potential energy 0? And you can call it anywhere, but there's kind of a clever choice. Actually, no, I think my clever choice makes me do a little more algebra. So I will let's let u equal 0 at the ground. U gravitational equals 0 at the ground. Notice that we need to know here the height h1 and this height final h final here. Is that on my sheet? Yeah. So those are the h's that go in u grav is equal to mgh, and we can find h1 and h final using we know the hypotenuse and one of the angles. So I think that the sine of theta is h1 over d, so h1 is equal to d sine theta. See that? Okay. So h1 equal d sine theta, and here h final is equal to d final times the sine of theta. Does that look right? Okay. All right. So those are the two h's that go into the MGH. So the final final gravitational potential energy is mg d final sine theta, and the initial here is mg d sine theta. All right. So a little crowded, but we can solve here for d final in terms of those other pieces. So let me rewrite it maybe. Mg d final sine theta minus 1/2 k d minus d naught squared, subtract mg d sine theta. So d final then is equal to 1/2 k d minus d naught squared over mg sine theta, and then plus the m, the g, the sine theta all cancel out, so we just get plus d. Not bad. Okay, I'm going to stop the video real quick right here so we don't record too much extra stuff.